what I'd like to do is give you a complete understanding of the project, a little bit of a smattering of the results, some discussion of what the public impact of it may mean going forward for all of us, and how we make successful midterms and decadal surveys and other things. And many of you are involved in upcoming missions, and hopefully some of the things that we learned on New Horizons will be a benefit. So let me start with a year ago, exactly a year ago, when this was the extent best image of Pluto, made by the Hubble Space Telescope. You know, we wrote papers about this image. We go forward after the flyby, and we're in a whole different regime, where the binary and the satellite systems surrounding it have been fully revealed, with a payload whose power is orders of magnitude more capable than any first flyby planetary reconnaissance, primarily because we built the thing in the 2000s. The previous payload that was sent on a first reconnaissance mission was a 70s era payload on Voyager. A little bit of history. Some of you sat through this tortured history. The earliest rumblings in the scientific community to reconnoiter Pluto began in 1989. When I personally went to Jeff Briggs, who was then the Planetary Division Director, which is Marine's equivalent, on behalf of the group that called itself the Pluto Underground, patterned after the Mars Underground of the early 80s, and asked to see if the Planetary Division would study a Pluto mission, and Jeff agreed to do that. That was just before Voyager arrived at Neptune. That study was called Pluto 350 because the spacecraft was to weigh 350 kilograms or less, which is a small spacecraft by planetary standards in those days. That second mission that S&D, or then called OSS, was in, flying a Cassini-class mission to fly by Pluto, Mariner Mark II. That was scuttled for, that houseboat was scuttled for a hamster called Pluto Fast Flyby, 35 kilogram mission, which proved unworkable. It was resurrected as Pluto Express, which got completely out of control on cost and became a multi-billion-dollar Pluto flyby. That was replaced by Pluto Kuiper Express, which was part of a combined program to do Solar Probe, Europa, and Pluto, all the same spacecraft. Therefore, all three spacecraft had to be radiation hardened and carry all the mass and rad hard parts and the expense of going to Europa. That didn't work out too well either. Ultimately, Ed Weiler, in his first tenure as AA, declared that Pluto was dead and NASA wouldn't look at it again until 2020. So we decided to call ourselves the Undead. And after about 90 days, we raised the white flag and put out an announcement of opportunity to compete the mission. And New Horizons resulted from that competition. The reason I'm going through this is to say that just like Europa, which has now been 20 years in the making, since 1995 when Europa was first put on the table, these things take a lot of work sometimes. And really, if it hadn't been for the support of the community, we would have never succeeded. Not just the people on New Horizons, but our competitors, people who were on the SSES, that were on the decadal survey back in 2002, 2003, many other committee efforts, many advisory panels, review panels, and just a lot of letter writing and other support from the planetary science community. And so as a community, we got this done. Why was there such interest way back 25 years ago in flying a mission to Pluto? After all, it didn't fit the pattern. It's not a terrestrial planet. It's not a giant planet. It appears to be a misfit, or it did initially appear to be a misfit. All the early things that we were learning when the technology got good enough to do ground-based and early space-based work on Pluto were enticing. Let me review a few of those. This is a 1990s era shortwave infrared reflected spectrum that shows many absorption bands due to methane, as well as carbon monoxide and nitrogen. And each of those three volatiles are in fact volatile and can generate substantial vapor pressure. Because Pluto's in an elliptical orbit, it was clear to us that it would have strong seasonal cycles as a result of just this. And this is a much more complicated situation than we had seen anywhere else. You know, Mars, for example, with two volatiles, the CO2 and the water, is complicated enough. When the mutual events took place, and Rick Binzel was heavily involved in that, we were able to get the size of Pluto to reasonable accuracy. And having known its mass already from the astrometry of the binary, we were able to determine its density was near 2 grams per cc. We've since learned, due to New Horizons, that it's a little bit lower. But the big surprise, which is still held up, is that it's primarily a rocky body. At the time, we thought it was about 70% rock with an ice mantle. We also knew from the specific angular momentum of the system that it looked like the binary had been formed through a giant impact, very similar to the Earth-Moon system. So from an origin standpoint, there was a lot in there for people. And then in 1988, the Kuiper Airborne Observatory did an occultation experiment that Jim Elliott was the PI of. There were also some ground-based campaigns for the same event that discovered the refractive signature of Pluto's atmosphere and even vertical structure in the atmosphere. So very long ago, at that time in the early 90s, we knew that this was going to be an interesting object. And that is what supported the ability to get those studies done and to see money poured into those studies year after year. But it never quite got Pluto to the top of the queue. What made the difference was the discovery of the Kuiper Belt, the largest structure in our planetary system, but most importantly, the discovery of Pluto's cohort. The fact that Pluto is not a misfit, it is simply the brightest, the first discovered, and the largest of a whole collection of small planets in our solar system, which outnumber the giant planets and the terrestrial planets combined and form a third class of object. And that was really the root cause for the 2003 decadal survey, catapulting what they called the Kuiper Belt Pluto mission to the very top of the median mission queue that started the New Frontiers program. Because it wasn't just about going to a fascinating object or pair of objects, but it was also about opening up the exploration of Kuiper Belt and this third class of planet in our solar system. We're having reliability problems with advancing it. So the decadal survey, you see the cover of it there, made this recommendation. We won the competition, and off we went. I will say, this is a different kind of mission than we're used to flying today. In the early days, when mariners and pioneers were doing the first missions in the inner solar system and even in the middle solar system, Voyager, there were missions with objectives like this. Today we ask much deeper scientific questions. This is really a mission of exploration. So the level 1 objectives, called group 1 objectives in this case, were very simple. Essentially to map the surfaces of Pluto and Charon. Remember, the small satellites were not known at the time that these requirements were written. To map the surface composition of the pair and to characterize the neutral atmosphere of Pluto and its escape rate, which at the time the escape rate is a hot topic. And there were many secondary objectives that deepen that, higher resolution stereo, thermal work, trace gases in the atmosphere, etc. And then there were some nice to haves at the bottom. And these are the titles of those requirements. They actually came in paragraph form with detailed specifications. We proposed on New Horizons, there are 15 objectives here. We proposed to do all but one of them. And that one that we did not propose to do was to search for a magnetic field. So we did not fly a magnetometer. We did fly 7 very competent scientific instruments on a small spacecraft, actually about 350 kilograms, the way this thing started. I will just talk about the functions of the instruments that we carried. Alice is an ultraviolet mapping spectrometer to study Pluto's atmosphere and to search for an atmosphere around Charon. Rex is radio science. Its primary objective was to do the temperature and pressure profile in Pluto's atmosphere through an uplift occultation technique that involved the DSN. PEPSI and SWAP are respectively MEV and KEV plasma detectors, whose job is to determine the composition of ions escaping from Pluto's atmosphere and to measure the escape rate by finding the balance point between the outflow from Pluto's atmosphere in balance with the incoming solar wind. LORRI is a panchromatic long focal length equivalent of the Voyager narrow angle camera for high resolution mapping and to extend the time base of the encounter from just a couple days to several weeks so that we can look for changes. On the surface, we flew the first student-built instrument on a planetary mission, at the time controversial, but today very popular. And then Ralph, which is our primary remote sensing suite, is a 4-color camera combined with an infrared mapping spectrometer that can do 64,000 locations at once from 1.25 to 2.5 microns, essentially the same band that I showed you, the ground-based result. And it also contains panchromatic cameras with the same band pass, just silicon CCD that LORRI carries. What were the challenges? First challenge for us was to meet the cost requirement. New Horizons was built and flown for 5 times less money than Voyager. Now, admittedly, it's only 1 spacecraft, not 2. But this was quite a challenge, and many people were very skeptical that it could be done. Several of those Pluto mission studies started off with the intention of being inexpensive, ended up being very expensive, and were canceled for that reason. Our second issue was the development schedule challenge because I received a phone call saying we had won the competition on the 29th of November, 2001, during the New Orleans DPS, for any of you who were there. I was literally pointed at a payphone and said, "There's a phone call for you." And the time from award to launch was 4 years and 2 months, which is a very short development schedule for a planetary mission. And we were not able to really slip that because, in fact, the January 2006 launch window that we ultimately flew in was the last Jupiter gravity assist window of the 2000s. Had we missed it significantly, we would have been launching about now. So we had to make both cost and schedule, and we were unable to trade between them. Launch vehicle development was a significant issue because this launch vehicle that we flew on, the Atlas V, was in development and not yet flown. So it also had to make schedule. It had to be successful in all of its first flights, every one, in order to be certified for a nuclear launch. We were tail number 10 in that program. Instrument miniaturization. Those 7 instruments on New Horizons weigh less than the imaging subsystem on Cassini, just the camera. And then nuclear launch approval for Galileo and Cassini had taken an order of a decade. And to do that on a 4-year schedule was another challenge. So we had a busy 4 years getting New Horizons built to the launch pad. We did that. We launched it in January of 2006. We flew to Jupiter on a direct descent trajectory, no Earth or Venus gravity assists. We arrived at Jupiter 13 months after launch. We used Jupiter for gravity assist, but also as a flight test objective to practice for the flyby of Pluto. And we were the 8th mission to Jupiter, and we did some very interesting, unique science, but that's a different talk. Then we flew across the middle solar system for 8 years with a very small flight team. Voyager, an extended mission to Uranus and Neptune, was 450 belly buttons. New Horizons was about 50. It's part of how you keep it inexpensive, is low-cost flight operations, because it's the gift that keeps on giving. For 9 years straight, we had low cost. We also did many things in the development of the spacecraft that also helped minimize the cost. We made many compromises, one of which I'll talk about later, which is the fact that it takes us more than a year to get data to the ground. During these 8 years that we cruised from Jupiter to intercept the Pluto system, the spacecraft mostly took care of itself. We pioneered extensive hibernation. Other missions have since adopted that, but it allowed us to have a much smaller flight control team. And when the spacecraft was hibernating, the flight control team was writing Pluto encounter software, both nominal and backup, as well as fault protection software for 150 faults that the spacecraft was capable of taking care of. It wrote 260 ground malfunction procedures to help the spacecraft in more complicated situations. So it was a very busy 8 years for the New Horizons team. I know I was asked, and I'm the PI, people asked me, do you work on New Horizons? It's out in the middle of nowhere. And we worked 52 weeks a year, all 8 years, to get it done, to get it all certified, to do all the steps that were necessary, not just to build an encounter sequence, to make sure it would work and could be certified to work. So this is the encounter. It's a 2-year-long flight operation. We exited hibernation for the last time on December the 6th, 2014, and began the encounter 5 weeks later, beginning of 2015. And the encounter operation, because of the long downlink, stretches to the end of this year, which is the end of our primary mission. On the front end, the spacecraft science was pretty mundane. We were still too far out in January of last year to beat Hubble resolution. But we were doing optical navigation to close the loop for our targeting. And we had some very tight targeting considerations to fly through the occultation shadows. And we were doing a hazard campaign to look for rings, dust sheets, satellites that could give us concern about our aim point. As it turns out, we found none of that. We were able to fly the best possible trajectory and sequence. We didn't have to pull any of the alternates out of the drawer. They would have lowered the science return. So we did that for about 6 months. Environmental characterization with our plasma instruments, the dust instrument, and optical navigation and hazards. We actually did do 3 trajectory corrections on approach. The last one at the end of June, very, very small tweak to the trajectory. And we ended up going right to the box that we wanted to fly through, a 60 by 100 kilometer box with a plus or minus 9-minute timing constraint on time of closest approach. Those sound like forgiving windows, particularly when you're used to things like trying to put MSL on Mars with a much smaller window, but we were aiming from 3 billion miles away. And if you give a public talk, you can tell people, because I checked the math, one of our engineers did it, going through a 60 by 100 kilometer box, aiming from 3 billion miles away is the equivalent of an LA to New York golf shot that lands in a soup can. And as to the 9-minute closest approach timing requirement, we actually arrived 87 seconds off schedule, by 1.5 minutes. So that's something that we're very glad about. The Pluto system has a very high obliquity, like Uranus. It's tipped on its side. And like the Uranus flyby in 1986, we came at it at a very steep angle. So in fact, on the 14th of July, when we flew the closest approach, we had closest approach to every object in the system within a matter of a couple of hours, all at once. And that was another challenge in terms of sequencing the encounter, because we had to divide our attention not just among 7 scientific instruments, but among 6 targets in the system, all of which got the biggest in the window at about the same time. We have, whoops. Oh, I see. Should be one more slide here, but there's not. Oh, there is, I see it. So there's a little faint arrow. This is where we are today in terms of the downlink. We just passed 50% of all the bits on the ground. It's going to take us through October, sharing the DSN to finish that. We have sent all the Group 1 data to the ground from the table that I showed you earlier. So the mapping spectroscopy, and the basic atmospheric data sets are all on the ground, but there's a great deal of data still to come to the ground between now and approximately 1st of November when we finish. The data sets are spectacular. We conducted about 550 observations in the system. We have the engineering records from all of them. No observations failed. And in many cases, we exceeded our expectations either by sequencing more observations than it took to meet the objectives, or by the end of the system simply being sort of rewarded. But we have vast panchromatic and color data sets. We have lots of stereo. We have composition maps at 512 different frequencies. The occultations work. We got the ultraviolet and radio occultations. The plasma instruments all worked. All of it was successful. This is kind of a family portrait taken a few days out of Pluto and Charon, the binary itself, and the two larger of the 4 small satellites. These are Nix and Hydra, respectively. I'm going to refer to some feature names on the surface of Pluto, and they're informal. They're names that we use inside the team. We submit them later for the IAU's consideration, but we've been a little busy the last 8 months since the flyby, and so we haven't done that yet. I'll say a little bit now about the science. These are images of the small satellites in order outward from the binary. Styx orbits closest to Charon, then there's Nix much larger. There's a scale bar here. So this is about 60 or 70 kilometers. Kerberos, and then Hydra. That looks a lot like Michigan. All four of the satellites turn out to have very high albedos and very similar albedos, approximately 70 or 80%, much higher than expected, and much higher than not only Charon at 35%, but even higher than most areas on Pluto's surface. This is surprising. We don't have the compositional spectroscopy on the ground yet, but we expect when we get it down in April, it'll reveal that they're made of water ice. We'll see about that. We do have some color imagery of the satellites on the ground. We do have enough. These aren't the best images, by the way, but it's a nice montage. We do have enough craters to age date the two larger ones. I'll speak to that a little bit. It's interesting that the architecture of the system looks to be little one, big one, little one, big one. Whether that's telling us something about the disk after the giant impact of the Pluto Charon system or not, I'm sure people will work on for a long time. We've also, through doing photometry, unresolved photometry on approach, determined the rotation periods of all four of the small satellites for the first time. None of them are synchronous. This was a surprise. In fact, they're rotating very fast compared to their orbit periods. Hydra is tumbling about 2 orders of magnitude faster, about 90 times faster than its orbital period, but even the others are quite a bit faster. What is exciting this system is a debate for dynamicists, but it's very different than what we find with giant planets. I'll just say a word or two about Charon. 1,214 kilometers across. Looks like a mid-sized icy satellite, but some interesting characteristics. Just to be brief about it, the first thing you may notice is this dark polar stain, this reddish stain. It's actually the same color as the vast Tholen units on Pluto's surface. And we believe that it could be the result of atmospheric transfer of nitrogen and methane from Pluto, which would impact the surface everywhere, but would cold trap at the poles. And then, subject to solar ultraviolet radiation, produce a Tholen that's inert. If this is correct, there should be a similar stain at the other pole, but because of Pluto's obliquity, we can't see that for about another 30 years. We do have some Pluto-like images that give tantalizing evidence that there is a dark region at the south pole, but that's not entirely conclusive. The other thing that you might notice immediately, other than there are a lot of craters, is this big extensional tectonic belt, which is interpreted as a potential signature of a former ocean of water that froze and the expansion created the tectonic belt. If you look a little closer at the craters, you'll notice many have bright ejecta rays, others have dark ejecta blankets. And what that's telling us about the impactors or the inhomogeneities of the subsurface is under debate. We looked very hard for an atmosphere for Charon. I just submitted the paper as first author. We used several different techniques, the most sensitive of which was ultraviolet occultation that limits the atmosphere below the picobar level, which is equivalent to the lunar atmosphere, which is an atmosphere but very, very, very low density.
I have a quick question, sorry. On that image,
Mike, please.
trying to think about
Mike, thank you.
the question simply, is this the face that Pluto sees?
This is the opposite face.
Okay, thanks.
Yeah. Okay, so we have age dated the surfaces. Actually, Kelsey Singer has done the work that I'm going to show you. Bill McKinnon's former graduate student. And we've had Stuart Robbins doing the same project, and they get results that agree. They've counted about 1,200 craters on the surface. They get a 4 billion year age for almost all models of the Kuiper Belt impactor population. We have enough craters on Nix and Hydra to do the same. They turn out to have similar ages. So for the first time, we can prove that the giant impact, or whatever created the satellite system of Pluto, was ancient and not recent. And when I show you imagery shortly of with signs of vast geologic activity on Pluto today, we know that we cannot appeal to the fact that the giant impact is the energy source and it only occurred recently. We now know that it occurred a very long time ago, and that any energy from that impact long ago dissipated. Okay, so on approach, we observe the system every single day for weeks. This is Pluto as it rotates. The color imagery at the bottom is what we call the encounter hemisphere. You might recognize the heart-shaped feature we call Tombaugh Regio. I'll have a lot more to say, particularly about the western lobe here that's informally called Sputnik Planum. But I also want you to notice that Pluto's far side, so-called far side, is very different morphologically, geomorphologically. We have better imagery than this, but I don't have time to show you everything. But I wanted you to know that these images have about 100 times as many pixels as the Hubble images. We also have color and composition data at low resolution on the far side hemisphere. So while we didn't have a second spacecraft to fly by Pluto and get the other hemisphere, it's a slow rotator, we do have a basic characterization of all the sunlit terrains. The same is true for Charon. Yeah, so this is the encounter hemisphere at about 900 meters per pixel. So this is about 500 times better resolution, linear resolution, than the Hubble image. And I'm sure many of you have seen this before. The striking thing from my standpoint is the variety of different terrain types. We have very heavily mantled North Pole. We have a vast glacial region, Tombaugh Regio. We have regions that are very dark and devoid of volatiles. They're the equivalent to your eye of the lunar mare. We have a rift valley, more extensional tectonics. These are almost radial, in fact, to Sputnik. We have large scarps that appear to be, we know that they're made of volatiles and appear to be in recession. We have a variety of different terrain unit ages that we've recovered, and I'll show you all of that in the next handful of slides. This is a view as if you were standing about 800 kilometers above this dark mare-like area that we informally call Cthulhu, looking back at Sputnik Planum. The length scale here is about 1,000 kilometers north to south. There's about 1 million square kilometers of terrain on Sputnik. We haven't been able to find a single crater. And we can invert that for a crater retention age, and all we get is an upper limit since we have no detections. But the upper limit's at 10 million years, so it's very young. Ringing Sputnik Planum on all sides are mountain ranges that suggest to our geology and geophysics team that this is in fact an ancient impact basin. These mountains tower as much as 5 kilometers above the plain. So there was just a story last week about Titans, giant mountains that are about 2 kilometers high. This much smaller planet has mountains up to 5 kilometers, 5.5 kilometers high. There are many things I could say about these mountain ranges, and they're individually interesting. But I want to instead turn to the glaciology for a little bit. This is the northwest quadrant of Sputnik Planum, where the ice fields abut the mountain ranges. And we see many interesting features. And most particularly, this slide is to show you that we can see glacial dynamics, that we actually see flow around obstacles. In addition, if you look closely, and it's too bad all the lights are on, but there is a polygonal or ovoidal pattern in the ice. I'll show it to you in more detail. You don't need to get that data. I'll be able to show it to you with another slide in a little bit. And we believe that what's going on is that the ice is actually convecting. Bill McKinnon has authored a paper that's currently in review at Nature, and which we expect a decision on very shortly, where it's done some very nice modeling to show the feasibility of this concept. This is along the mountains on the eastern side of Sputnik Planum. By the way, the green box is always for context. So we move from over here to over here. And I just want to point out the chute and this flow of material that's come out of the mountains down the hill into Sputnik. We appear to be seeing drainage on the other side, some signatures of drainage. So we are seeing a real glacial cycle taking place on a fantastic scale and active today. This is the image that I wanted to show you that has more detail, where you can see those ovoidal patterns throughout Sputnik. This is a ratio image of some high phase to low phase imagery. It just shows the forward scattering nature. Where it's brighter, it's more forward scattering. John Spencer put this together just a couple of weeks ago, and it's just stunning, the complexity of what's going on there. And I'll just leave it to all of you to just look at that for a minute. And I want to encourage you to take a look at the week before last issue of Science, New Horizons data. Were on the cover. There were 5 papers on the geology, compositional data sets, the atmosphere, the plasma, and small satellites. Everywhere we look, we see complexity. We see it in the color data. We see it in the variation of surface compositional units. There are very stark gradients all across the planet, and a lot of work to be done. NASA will issue a Rose's call for DAP proposals later this year. Our first PDS delivery is about 2 weeks away, and we're on track for that. And so you may become involved in some of this yourself. This is an example of some particularly strange terrain on Pluto's surface. Near the terminator, the field that you're looking at is about the size of western Colorado. And what you will no doubt notice, or already have noticed, are these aligned, bladed terrains stretching over hundreds of kilometers with characteristic separations of a few kilometers, characteristic heights of a few to 500 meters. Turns out they are made of methane. And we don't know if they are giant methane crystals that are growing, or if this is what is left over after you scour out the material in the valleys between them. It's a hard problem, and really smart people are working on it. The more people we can get on it, the better, because this type of terrain has not been seen elsewhere in all the exploration we've done, the icy satellites, or anywhere for that matter. We also have pretty good evidence from stereo imagery that we're seeing summit calderas, a number of them, like this one, in which the mountain is about 150 kilometers across. The age data is very young compared to the age of the solar system, very few craters on the surface. The caldera itself is 10,000 feet deep. And I don't believe that there's any structure like this between Mars and Pluto that we know about from any spacecraft mission. If you like craters, there's plenty of old terrain also on Pluto, very rugged terrain. This is actually at the borderland between southwest Sputnik Planum and Cthulhu. These are saturation cratering levels. And again, Kelsey and Stewart have done the work and have age dated. The oldest terrains like Cthulhu are just as old as Charon, 4 billion years old. The youngest terrain is Sputnik Planum, less than 10 million years old, but importantly, Sputnik is no anomaly. We see intermediate age terrains as well, indicating that Pluto has been active a lot over the entirety of 4 billion years. And that's a puzzle because of its small surface area to mass ratio. We also studied Pluto's atmosphere, which you can actually see in this forward scattering image. It reveals itself through haze layers that were speculated about, but never discovered from the Earth. We count over 24 haze layers stretching up over 250 kilometers in altitude above the surface. We actually made this image not to look for haze specifically, but to study the scattering properties of the surface. And there's plenty of data there too. These concentric haze layers were not predicted. The possibility that there was haze was predicted, but the very regular concentric spacing was not. The temperature and pressure in Pluto's atmosphere is very reminiscent of Titan's, not Triton, Titan's upper atmosphere, where the detached haze layers are seen. And of course, they're both nitrogen-rich atmospheres with methane. So our atmospheric team is having a great time with this and writing papers about it. In fact, we have a special issue of Icarus in which we've submitted now almost 20 papers. That'll be coming out later this year. We have a theory for the regularity of the haze layers, and that has to do with buoyancy waves, gravity waves, in Pluto's atmosphere launched over the mountain ranges. And we can make that work. Whether it's actually what's going on or not, we'll see if it has competitors, but that's the first idea. When we look back at the haze, this is a true color image, it's not stretched. It's beautiful, but because it's very reminiscent of imagery of Earth's atmosphere, it's actually blue. It's me scattering by very small particles, and it really is blue. From the atmospheric occultation, we made a major discovery that the upper atmosphere is much colder than we thought, about 40 Kelvin colder. Instead of being 110 or so, it's about 70 Kelvin. And because it's colder, scale heights are smaller, and so the atmosphere is more tightly bound in the gravitational potential well than we had expected. Additionally, because it's colder, the atoms in the Maxwellian are less energetic, and therefore they're moving slower and less able to escape. And when you combine those two effects, our current estimates of the escape rate from Pluto's atmosphere are vastly different than pre-encounter predictions. Pre-encounter predictions were 10 to the 27 to 10 to the 28 molecules per second, like a comet. The actual Pluto atmosphere is down at the level of about 10 to the 25th, and the dominant escape species is actually the methane, not the nitrogen, because the methane is lighter. It's preferentially able to escape above the exobase compared to nitrogen. As I said, we've been working hard on publications, in addition to just getting the data to the ground and getting it ready for archiving and getting results out to speak at meetings like DPS and AGU and recently LPSC. Many of you remember the Voyager 90-day reports that were turned in 3 months after the flybys of the giant planets. We worked very hard and turned our first paper into Science 3 weeks after flyby, and it was published 90 days after the flyby on the cover of Science in October. And then just 2 weeks ago, as I said, we had 5 papers in Science. Those guys papered in Nature, and there's about 20 papers we've submitted to Icarus. So as a recap of the project, and then I have a few other things to say. I think we achieved a breakthrough on mission cost and development time that can be very beneficial as an existence proof that we can get small missions to very far away places and do exploration at unheard of costs compared to 60s, 70s, and 80s models. All the flyby objectives were met or exceeded. The first PDS archiving delivery is 2 weeks away, as I said. There's going to be a ROSES call for data analysis programs later this year. We're working hard on publications, so I'm sure there'll be a lot more very soon. I want to say a little bit about our proposed extended mission. The deadline for extended mission proposals to senior review is in about 2 weeks, the 15th of April. We'll be turning one in. And I'm sure many of you know that the centerpiece of that mission is to fly on to a intermediate-sized Kuiper belt object about 1 billion miles farther than Pluto. So let me tell you some of the details of that. This is the object, some of the details for the object over here. It doesn't have a name yet, just the designator. 2014, the year it was discovered by our team using the Hubble, MU69. So we just call it MU69 for now. I want to have a naming contest, and Jim Green kept delaying me on that. Bless his heart, because we wouldn't have got this mission done without Jim. But he kept saying next month, and finally I told him, I said, in the New Horizons team, we now call this object Jim Green, until you change it. It's a small object compared to Pluto, which is of order 2,300 kilometers across, but it's a very important size scale. So here, compared to the state of Massachusetts, is this object, and if you look very hard, I know the room's not dark enough, but that's Comet CG67P that Rosetta's orbiting. This thing is about 4 orders of magnitude more massive, and it's intermediate in a logarithmic sense between comets and small planets, and so it's going to help us a lot in understanding early accretion. This is a cold classical KBO, meaning it originated where it is orbiting now. It's not a participant in migration, so it is a bedrock sample, if you will, of the nebula at 44 AU. It's always been there, it's always been cold, it's never been processed the way the comets that we observe when they come to the inner solar system are. And so it is no doubt the most primitive object that we will ever have studied. We have already done the preliminary planning for a flyby, and we know what we can achieve, and it's going to be spectacular. In fact, we believe we can go a lot closer than Pluto, so we'll have much higher resolution imaging and imaging spectroscopy. We will search for a coma, although conventional wisdom says there won't be one. We will nonetheless look very hard. But I want to say that the extended mission proposal that we're turning in is much more than just a flyby of MU69 Jim Green. By the way, that flyby is on the 1st of January 2019, for reference. We've thought very hard about what our spacecraft can do as an observatory in the Kuiper Belt. And there's a large amount of science that goes with this mission in addition to the close flyby of MU69. We passed close enough to over 24 KBOs to study them in ways that you cannot from the Earth, even with future telescope systems. For example, we will measure their phase curves and get their surface microphysical properties so we can put MU69 in context. We'll also get phase curves of several other Pluto-like small Kuiper Belt planets like Maki, which you have to be in the Kuiper Belt to get the range of phase angles. You cannot do it from down in the inner solar system. We will also observe objects to get their shapes at a size scale that cannot be measured with Hubble or JWST or any other known technique within current technology. We will look back at almost 20 centaurs and KBOs taking advantage of our very high phase angle, looking back at them in forward scatter geometry to look for evidence of ring systems like were discovered a couple of years ago around Trikla, which was a great surprise. The centaur escapee from the Kuiper Belt could have a ring system. We're going to find out if that's typical or if that's rare, because we have a sensitivity in many cases to find ring systems that are 10 times less dense than the particulate assemblage around Trikla, as long as we understand the photometric phase properties of the individual particles. We are going to do Voyager-like science, but with plasma detectors in the heliosphere out there that are 1,000 times more sensitive than the Voyager instruments. And when Fisk was in this room, he'd love it. It can pick up ions, interstellar pickup ions, and we're carrying the first dust detector into the Kuiper Belt, which is going to be great science. And by the way, most of us in the room are probably not interested in the heliosphere professionally, but if you're interested in Kuiper Belt objects and surface weathering, then you're interested in those data sets being collected, because we want to understand what's happening to those surfaces from a radiation standpoint. And New Horizons is going to contribute to that in a big way. We've been asked by SMD to also propose to repurpose the spacecraft for astrophysics after the MU69 flyby, that NASA would conduct ROSIS calls in the astrophysical community to use our UV spectrometer and our imagers to do some kinds of astrophysics. They had a community white paper that was written last year, and we're making it available. We've got the fuel and the other resources to do that after the flyby. So we're going to do a lot of science. Those observations are already planned. You can see they stretch across the entirety of the 5 years from now until 2021. There are a lot of observations. It is a really intensive mission, and I hope it's approved. And I want to close by just talking about what it was like. It's been a generation since a first flyby was conducted, and for almost everyone on my team, it was an incredibly special experience to see Pluto turn from a point of light into a planet before our eyes after having worked on it for 15 years, to see it happen in a matter of weeks. And this is actually a picture at the moment that the first really high resolution image was projected. It was staged. NASA asked us to actually have the team there, get the image ready, and then put it up and see people react, because they wanted to put the scientific emotion into the image. And this is actually what was happening in the room at the Applied Physics Lab. It was if you ever get a chance to be involved in something like this, don't turn it down. It's well worth the 15 years, hundreds of plane flights, putting up with 15 budget cycles, all those things.
I would agree.
Yeah. Thank you, Jim. It's also something that we work very hard to do, and we worked for years to plan how we can engage the public, and we were very successful at it. As one metric, APL, which is mostly responsible for missions that they don't want anybody to know about, and Vince occasionally does a mission like Messenger that gets some public attention, was inundated with thousands of visitors, people who wanted to be there at the flyby. Very reminiscent of Voyager at the giant planets, maybe even on a bigger scale. But beyond that, there were so many other metrics of how the public reacted to this, and I don't just mean that we got the Google Doodle, which was cool. I had said for 15 years, Bill remembers this, he's been on this team since day one, so it's Rick, that we would make the cover of the New York Times the day after the flyby. We would make the cover above the fold, and we did. But we were on the cover of 458 newspapers by NASA's count, the same morning, above the fold, on every continent, including Antarctica. We were on countless magazine covers, from National Geographics to astronomy magazines. I'll tell this story at the public talk tonight. My next door neighbor, whose PhD is in electrical engineering from University of London, emailed me about a month before the flyby and said, Alan, in our house we take 6 magazines every month. 5 have come so far, and you were your mission on every single one. He said, the 6th one is Cosmo. If you're on the cover of that, I'll kill myself. So, we weren't. But let me also say that NASA countered, and we received an order of magnitude more web visits than MSL on landing day on our flyby day. 1 billion visits to our website. It's an incredible connection that we made with the public. Part of it's Pluto, part of it's exploration, I think. Part of it's a lot of hard work. But I think it shows for all of us as we think about future missions that if you work hard, you can really engage the public. But in addition, people really like seeing something for the first time. As much as they like going back to Mars, back to the Moon, back to other places, and I know Ocean Worlds is going to be spectacular. And for a lot of people, if we can get an Ice Giants mission, that's going to be really engaging. But going new places just has its own character. And I hope that as we get into the next decadal cycle that we talk about the diversity of planets in the Kuiper Belt and the possibility of doing more missions like this to study that class of planet, or perhaps instead to come back to Pluto in the orbiter because it's a very dynamic place. I think I need help because I don't have a laptop up here. This is a high-resolution movie of a flyover that starts in Sputnik Planum. And if you can start that movie by clicking the button on the screen, 70 meters per pixel, 70 kilometers across the screen because it's 1,024 pixels. These are the ovoids in Sputnik Planum. You can see their boundaries. You can see mountains sticking up. There's the shoreline with mountains to the northwest of Sputnik Planum. Chaotic mountain blocks, possibly created by that basin formation. Out northwest, beyond the mountains, into some badlands, you can look into the craters and see that Pluto's heart is layered inside the planet. We see both bright and dark layers, and these are mantle terrains off towards the pole where the movie stops. And with that, I can just say thank you for taking the questions.
Thank you, Alan, for your questions. I'm sure there are.
Hey, Alan, awesome talk, Ocean Mission. I hope to do this one day. Maybe I can get that 6 magazine Cosmo checked out the cover and engage our audience. In seriousness, though, one of the things that you hit on earlier was, this is a demonstration of lower mission costs. And one of the bullets, you coupled mission cost and development schedule. To what extent do you think that is one of the key drivers of the UK being able to achieve the low cost versus some of the other items that you talked about? How would you rate the relative importance of some of the measures that you spoke about?
I think the most important driver is the fact that we had to stick to schedule, or not have a Jupiter gravity assist and there would have been a 14-year flight to Pluto, was highly motivating. And the fact that we didn't have a lot of time means we didn't have a lot of time also to Christmas tree the mission. But I think the most important things were the first discipline. When we sat down as a proposal team, we thought a lot about how to win, but we also thought a lot about how to succeed to make sure that once we won it, we could actually build it and not get canceled, as had been the characteristic of Pluto missions. And so it took the ability to say no a lot, and that was never any fun because you can always do better. That was very important. We made quite a number of compromises. The telecom system is 10 times slower than Voyager, so it takes 16 months to get the data home by intent. We actually bragged about that point in our proposal, by the way. We wanted to show examples of where we made compromises to make it fit in the budget. We used a spare RTG from the Cassini Galileo program, rather than take a newer technology device or build a new one. We took a 20-year-old device. And we made quite a number of other decisions, including a very small science team. All those things went into actually having a local transmission, so of hibernation, as an example. I also said it took all of them. It could have been very easy for this to be $1 billion or $1.5 billion, and it never made it to the launch pad.
What was the total cost of it?
For the prime mission, $722 million in real year dollars.
We're not done. We're still in prime.
We're still in the prime mission.
John, congratulations again to you and the team. I remember a time when I was PFF or Pluto Express and was part of this dream. It sounded like the way to go. As you say, I think looking at new places is something that we have to do. And definitely, we saw it with also Rosetta this year, landing the comet and the asteroid, that you can engage the public on things that seem, far away or distant or not easily understood. I want also to commend you on the outreach in public, not just because we were on the magazines, but we had this experience also with Rosetta, and when you tell the people what's going on and you bring them to the creation of the space mission, it's as if they were part of it, and it's much better than you just throw things at them at the end. So I think this is very important. The public is there that support us, both psychologically or whatever, but with the funds, and so they deserve this kind of return. And when you get there, it's not just the science community that deserves to be surprised, it's also the public. So really this last part of showing how an impact, what's the impact on the large public, not just the science community, is really very important. So
And I said this at LPSC last week, we touch people's lives with this stuff. There's rarely a week, even 8 months after the flyby, when I don't get a letter from some parent about how New Horizons turned their kid on to science or engineering. And I've had people come up to me in public blogs and be emotional about it. So, and I don't think that's unique to New Horizons. We can do this as a community. And it's a public good in addition to making sure that the taxpayers are excited about what we do.
Did you actually also get the question, so is Pluto a planet again?
Yes, I thought this was going to be the first presentation I'd give in which I wasn't asked. Right, I get that a lot.
I liked your explanation.
Thank you.
It's one of the biggest of a whole new.
Biggest that we know.
So if you actually want to know my opinion about that, my favorite, as you know, what the IAU did is produce a really difficult definition of work because it produces many conundrums. It's primarily based, if you write the equations out, it's very steeply biased in heliocentric distance. The Earth, for example, in the Kuiper Belt cannot clear the zone. So identical objects qualify differently in different orbits, and that's a crazy classification system. So I actually like a really simple classification system, which I call the Star Trek test. You watch Star Trek and they arrive someplace new and turn on the viewfinder or the bridge. You and the audience know within about half a second usually what you're orbiting, whether it's a planet or a star, a spaceship or an asteroid or a comet. And I think that's good enough. I think that's why the public is so talkative about this 10 years later, is it didn't make sense to them either. Probably overstated my point.
Yeah, amazing stuff, so many questions. My brain's still fixated on something that you said early on with the cold trapping of the methane and the nitrogen. And perhaps it's a too detailed question, we can go to a chalkboard later or something. So my brain always sort of thinks of Io and Europa and the leading and trailing hemisphere dichotomy there. Did you see any leading or trailing hemisphere dichotomy given the Pluto Charon system and the possible atmospheric transfer there? Or was it just polar?
We don't in terms of color, if that's what you're asking about.
Well, color would obviously be a nice indicator, but spectroscopically in terms of composition, do you see any?
No, in fact, Kim Enico's done some very nice work, and so has Will Grundy, on exactly that question. And we don't see compositional color or albedo differences that are hemispheric, leading, trailing, or planet, anti-planet, satellite, anti-satellite. We don't see any of that. We do see the different faces of Pluto, the Charon facing, Pluto facing, have different character to them. There are quite a number of those Mare-like regions on the far side, with really only one on the entire hemisphere. Cthulhu is also the largest of them. So there are some differences. I don't know if they're necessarily related to that geometry. It does look like, and a number of people worked on this, including Francis Nemo, that talking about Regio and Sputnik Planum are very likely to have caused polar wandering, and that it's not centered on the anti-Charon point for no reason. It's not random. Right? It looks like both the obliquity and the longitude are due to a close feedback between the gravity anomaly there and the tides between Pluto and Charon.
So the one feature that
Actually,
So the one feature that looks like a frozen nitrogen lake. So does that indicate that at one time the pressure was great enough to make that a liquid?
Yeah,
Liquid
that's our
actually
hypothesis, and spoke about this at LPSC. There are a number of features on the surface that are consistent with the flow of liquids in the past, and there's at least one feature that sure looks like a frozen pond or lake. It's 20 kilometers in scale, and we have a theory for that. Pluto's, and Rick Binzel gets a lot of credit for this. He wrote a paper that wasn't the climate evolution paper, but the paper that really looked at the energy balance with his student, Sir Earl. Pluto's obliquity, as I said, is very high. It's about 120 degrees currently. But Pluto's obliquity has a 4 million year cycle with an amplitude 10 times bigger than what drives the Milankovitch cycles on the Earth. It's back and forth by 12 degrees. And this, combined with a precession, can create vastly different energy deposition patterns on the planet, which can drive the temperature and pressure, in extreme cases, above the nitrogen trigger point, to as high as 250 millibars. It's 40 times the atmospheric pressure of Mars. So whether that's right or wrong, we do have evidence that we do see features on the surface that look like they were caused by running liquids or ponded liquids. And there may be other reasons for how we got that to happen. Impact generated atmospheres that were short-lived is one thing that comes to mind. Some of them could be very paleo and date back from the earliest days. But that pond is actually in the mountain range we call Palidrissy to the northwest of Sputnik Planum. And so we don't find really any craters there. That's fairly there. Phil, did you have questions?
Well, I think you just answered it. I was just curious to come back to what is the energy source for this recent resurfacing that I think you just answered.
So, Bill's paper, and correct me or add this, Bill's paper to Nature says that we can do it with chondritics, just radioactive. Another idea that I like a lot is that latent heat release due to the freezing of an internal ocean could also power a lot of this.
Thank you very much, Alan.
Okay, thanks.